Welcome to a new video from Metrohm Germany. My name is Sandro Haug, and in this video I will talk about electrochemical impedance measurements on lithium-ion batteries and the related important practical issues which have to be considered. Let's have a look at the topics of this video. First, we will discuss the basic design and working principle of a lithium-ion battery. Then I will give you an overview which parameters of batteries can be measured using impedance spectroscopy. After a very brief introduction to this measurement technique, I will explain how a typical lithium battery can be described with equivalent circuits. And the important practical issues we will go through step by step. Which frequency range is needed? Measurement time as an important factor. Temperature dependency. Noise and how noise can be avoided during an impedance measurement. And to give you a practical example, we will measure a lithium-ion battery in a 3-electrode setup at 2 different temperatures. Let's start now with the basic operation principle of a lithium-ion battery. A conventional lithium-ion battery consists of 2 electrodes, a liquid electrolyte and a separator between the electrodes, to avoid short circuit. The separator is an isolating membrane which is permeable for lithium ions. It is soaked with electrolyte, which consists of dissolved lithium hexafluorophosphate in organic carbonates, in particular mixtures of ethylene carbonate with dimethyl carbonate and propylene carbonate. The negative electrode consists of a copper foil which is covered by graphite as active material. The positive electrode consists of an aluminium foil which is covered with, for instance, lithium iron phosphate as active material. There are also many other active materials like lithium cobalt oxide, lithium manganese oxide, or lithium titanide oxide, used in commercial batteries, and of course research for new materials is still going on. After assembling the battery, the first charging follows. While charging the battery, delithiation occurs at the positive electrode, and lithium cations move through the electrolyte and separator to the negative electrode, where lithium intercalates in graphite. During this first charging process, the surfaces of the electrodes react with additives, the electrolyte and lithium, and form the so-called solid electrolyte interface, SEI, on both electrodes. The role of the SEI layer involves the prevention of further electrolyte decomposition to maintain cycling ability. During discharge of the battery, the movement of the lithium cations goes the opposite direction. They move from the negative electrode, the anode, through the electrolyte to the positive electrode, the cathode. The basic principle is quite easy to understand, but to develop batteries and the components of a battery is quite demanding, and also proper electrochemical measuring techniques like impedance spectroscopy are needed to support the development process. So what can be measured with impedance spectroscopy? Or in other words, why is impedance spectroscopy such a valuable tool for battery researchers? Because the total battery, its components, and the occurring reactions inside the battery can be examined. Here are a few examples. Transfer number and ion conductivity of electrolytes. The better the conductivity, the lower the resistance. The electrochemical window of the electrolyte can be determined. That means at which potential starts decomposition of the solvent. McMullin number of the separator. This parameter explains the performance of a separator. Tortuosity of the pores of the electrode materials. The higher the tortuosity of, the more difficult the lithium ions can move in the electrode material. And it is also possible to characterize layers, for example the thickness of the solid electrolyte interface. In the following slides, I will give now a very brief overview of impedance spectroscopy. The most important advantage of impedance spectroscopy as measuring technique is that the sample is neither influenced nor destroyed during the measurement. So consecutive measurements on the same sample, like measurements at different temperatures or charge levels of the battery, are possible. And it's also a very valuable tool to characterize aging effects of batteries and their components. Impedance spectroscopy is an AC technique, which means that an AC voltage or an AC current with a very small amplitude of a few millivolts or milliamperes is applied to the battery. In this video, I will only focus on the potentiostatic impedance spectroscopy, where a small voltage sine wave is applied. The battery responds with an AC current with the same frequency to the applied AC voltage signal, according to the processes which get excited by the applied frequency. The amplitude and also the phase shift of the current signal will be different from the AC voltage signal. As you may know, the current response of a capacitor to an applied AC voltage signal is shifted by -90 degrees. So a phase shift in the measured current response indicates that there are capacitive components in the battery existing. With the values of the applied voltage sine wave and the values of the corresponding current signal, the AC resistance, the so-called impedance, is calculated. During an impedance measurement, the amplitude of the AC voltage keeps constant, but the frequency range is changed from megahertz to the millihertz range. That's the reason why the technique is named impedance spectroscopy. At the end, a measurement consists of around 50 to 70 frequencies with the corresponding calculated impedance values. Why do we need to apply such a wide frequency range? Because on the electrode surfaces and in between electrodes there are different processes with different speed occurring. Processes like diffusion of the lithium cation are slow, and on the other hand, the charge transfer reaction, where the lithium cation gets reduced, is comparable fast. The fast processes respond to high frequencies, and the slow processes respond to low frequencies. So by applying a wide frequency range, all processes inside the battery, from fast to slow, can be identified, measured and quantified separately, even when they are occurring in parallel. I already mentioned that for each applied frequency, the impedance value is calculated. The data points can be plotted in different ways, and the most common used plots are the Bode and the Nyquist plot. In the Bode plot, the magnitude of the impedance Z and the phase angle, which means the phase shift between the current and the voltage signal, are plotted versus frequency. The advantage of this plot is that you can withdraw the values for each single frequency, and you easily determine where ohmic behavior or capacitive behavior exists. Pure ohmic resistances show a phase angle of 0 degrees. This corresponds to electrolyte conductivity or charge transfer reactions in the battery. Phase angles up to -90 degrees indicate the existence of a capacitance like the electrode-electrolyte double layer. Phase angles between 0 degrees and -90 degrees indicate the coexistence of ohmic resistance and capacitive behavior or diffusion processes. The Nyquist plot, displayed on the right side, contains the same information, but it's plotted in another way. The imaginary part of the impedance, minus Z double prime, is plotted versus the real part of the impedance Z prime. The mathematical knowledge and how the plot is deducted is not part of this video. This information is provided in our impedance course. The Nyquist plot of the frequency is not displayed anymore, so you can just estimate the frequencies. The data points on the left side belong to high frequencies, and the data points on the right side are measured at low frequencies. The first impression is that information gets lost by using the Nyquist plot, but there is one very important advantage of this plot. the researcher gets a very good overview of the processes occurring in the battery. To explain this, we will have a look at the typical impedance measurement of a lithium-ion battery measured in the two-electrode setup. The distance of the curve from the y-axis corresponds to the electrolyte conductivity. In our example, it's 11.50. Then you realize that there are two semicircles emerging in the measurement. The first semicircle is caused by the sum of the SEI layers, and it corresponds to the lithium-ion transport through the SEI layers. The second semicircle corresponds to the sum of the charge transfer reactions at the electrode-electrolyte interfaces. The semicircle is followed by a straight line, which reflects the mass transport in the battery, the lithium-ion diffusion in the electrode and the electrolyte phase. So the researcher gets a very fast overview how many processes and which processes are occurring, and he can also determine the values. For instance, the diameter of the semicircle corresponds to the resistance value. So the diameter of the yellow semicircle, which corresponds to the SEI layer resistance, is 60.5 minus 11.5 ohm, which equals 5 ohm. Will the SEI layer increase? By cycling, the diameter of the semicircle will grow. It is possible to quantify the values of the battery components and the processes at once. To do this, an equivalent circuit needs to be created. You can see an example of a typical equivalent circuit of a commercial lithium-ion battery in the lower part of the slide. Each component or process of the battery is described by so-called equivalent circuit elements. For instance, the SEI is described by a resistor and a capacitor. The resistor element is used to describe the charge transfer reaction rate or the conductivity, and the capacitor element describes the solid-liquid interface. A Warburg element, shown as W in the circuit, is used for diffusion processes. So by knowing the components and ongoing reactions, the researcher can build the equivalent circuit for the whole cell. By using the fit function in the evaluation software, the value of each used element will be determined. So the researcher will get values of the resistances of the SEI layer, resistance of the battery electrolyte, kinetic information via the charge transfer resistance, and so on. By measuring, for example, the battery at different temperatures, what we will do later on in this video, the values of the elements of the equivalent circuit will of course change. A lower temperature will decrease the conductivity of the electrolyte, which will be reflected by a higher electrolyte resistance. Also, the charge transfer reactions of anode and cathode will be slower, which can be directly measured by the increased charge transfer resistances. Now let's have a look at important practical issues. Frequency range. The used frequency range plays an important role in impedance spectroscopy. It's like the used wavelength range in optical spectroscopy, which means that the proper frequency range needs to be chosen to see the object you want to measure. To examine diffusion processes, frequencies down to 1 Hz or to the millihertz range are needed. On the other side of the frequency range, the high frequencies around 1 MHz are needed to determine the conductivity of the electrolyte. For batteries containing a liquid electrolyte, a maximum frequency of 10 kHz as highest frequency is sufficient, but when it comes to all solid-state batteries, a higher frequency range is needed to get all the information of the sample, because the processes in the solid electrolytes are much faster than in liquids. This plot shows a measurement of a solid electrolyte model. The solid electrolyte consists of grains which are in contact with each other at the grain boundaries. Because the resistance inside the grains is different from the resistance of the grain boundaries, two semicircles in the high frequency range exist. The first semicircle represents the contribution of the grains, and the second semicircle represents the contribution of the grain boundary. If the measurement would have been started at 1 MHz, all the information about the grain resistance would have been lost. Time. One of the most important rules doing impedance spectroscopy is stability. During the measurement, the device under test must not change. In basic research, it can happen that the battery itself is not stable over time. So at least for the measurement itself, a degradation or change should not occur. So it is important to keep the measurement time short. This can be done by measuring the anode and cathode simultaneously by using a 3-electrode setup. It takes just half of the time, and additional wiring effort can be omitted. And the researcher can be sure that both electrodes are measured at the same conditions. Temperature dependency. As all chemical reactions, also electrochemical reactions depend on temperature. A change in temperature has a direct impact on reaction kinetics and mass transport, which is expressed by the formula of the reaction rate constant and the diffusion coefficient. So it is very important to keep the temperature constant during the running impedance measurement. This example here shows two different measurements. The red curve shows a measurement at a constant temperature of 15 degrees Celsius, and the blue curve represents the same measurement on the same sample, while the temperature was increased from 15 degrees Celsius to 20 degrees Celsius during the measurement. Because high frequencies are measured very fast, the temperature change was neglectably small for the data points building the semicircle. They have been measured in a few seconds. But lower frequencies need much more time to be measured because the lower the frequency, the longer the measurement time. That means that the evaluation of the low frequency range where mass transport occurs of this measurement should not be done due to the temperature drift. Noise. There are two different kinds of noise: external noise and noise caused by the measurement itself. To reduce external noise, you just use a suitable Faraday cage, bring your battery inside, and you are on the safe side. Noise caused by the measurement itself has to be reduced by cable positioning. The cables for the working electrode and the counter electrode are the current leading cables. Due to the relatively high AC current during the impedance measurements, these cables emit a magnetic field, which can induce noise in the voltage measuring cables, labeled with RE and S in the picture. In worst case, the setup works as transformer. To cancel out this transformer effect, it is needed to position the cables in the displayed way. The current leading cables and the cables which measure the voltage have to be twisted. Both pairs have to be separated to a maximum distance. But why? By twisting the current leading cables, the emitted magnetic field is much smaller, and by twisting the cables for the potential measurement, the affected area is much smaller. More about this effect you will learn in our impedance course. One clever technical solution to reduce noise pickup is to amplify the measured signal in the vicinity of the sample. This is done by an external electrometer, which is located very close to the sample. From this place, the noise pickup is reduced to a minimum. Before starting the experiment, I want to explain which hardware features a potentiostat should have if you want to use it for impedance measurements on batteries. Maybe you have already some potentiostats in your lab and you have to choose one, or if you are planning to purchase a potentiostat, this information will help you to buy the most suitable instrument. High current range. Already batteries in the exploratory research status, depending on their design, can deliver high currents. Therefore, the potentiostat should be able to measure and apply currents in the amp range. Second sense electrode. As you have already seen, a second sense line enables the measurement of the second electrode at the same time in a 3-electrode setup. This saves time and you can measure both half cells simultaneously. Frequency range higher than 1 MHz. Normally, a maximum frequency of 10 kHz up to 1 MHz is sufficient for batteries with liquid electrolytes. But in all solid-state batteries, processes are much faster. So for this field of application, a frequency range higher than 1 MHz is needed. An external electrometer close to the sample is recommended to reduce the pickup of noise. A cell isolation and cell button should be provided by the potentiostat. In case of urgency, pressing the cell button is the fastest way to disconnect the cell manually. Input for temperature sensor. This is very useful due to safety reasons, but also to check and record the temperature of the battery during the measurement. Now I will present you the setup for the measurement we will use. For the experiment, we will use the Potentiostat Vionic because it provides all the previously mentioned hardware features for impedance spectroscopy. Starting from high current over second sense, high frequency range, external electrometers, safety features, cell button, down to thermocouple input connector for temperature measurements on the backside. As a measuring cell, we will use the TSC battery in combination with a temperature controlled stand. With this combination, electrochemical measurements can be done in a temperature range from -40 degrees to +100 degrees. The cell is small, very handy, easy to assemble, and it fits to all glove box chambers. After plugging the cell, the temperature is being adjusted to the set value. Let's have a closer look to the battery cell, the TSC battery. It consists of two current collectors, the upper one and the lower one, and in between these current collectors the electrodes are located. The electrode on the bottom side is the anode. It consists of lithium metal, and the electrode on the upper side, this is the cathode. It consists of lithium iron phosphate. In between of these electrodes there is the separator, which is soaked with an electrolyte, and the separator is a Watsman glass fiber filter. The spring is used to adjust the pressure on the cell. The temperature of the cell is set to 22 degrees Celsius and the temperature is constant for 15 minutes. So I already started the measurement and now we are recording the OCP potential. It's about 3 volts and 245 millivolts. This is quite constant, so I accepted the value and now the measurement starts at the OCP potential, which we measured previously. In the bottom part of the software you can see the plots. There are 4 plots for the impedance measurement, 1 Nyquist plot for the working electrode, the second Nyquist plot for the counter electrode, and 2 Bode plots for the electrodes. In the Bode plot you see displayed the magnitude of the impedance and the phase angle with respect to the frequency. As measuring parameters we are using a starting frequency of 80 kHz and the last frequency of 100 mHz and an amplitude of 10 millivolts. This amplitude is sufficient. It should not be higher that the battery is kept in constant state, in a steady state. And here the frequency which is measured is displayed. Now we are at 8 kilohertz. And in the down part you see that the plots are building up, and to keep the overview quite nice, we are also able to merge plots. So I merged the Nyquist plot of the working electrode with the Nyquist plot of the counter electrode, and we have all plots in one graph now. This measurement will take now about 2 minutes till it's finished. So the measurement at 22 degrees Celsius was finished. I set the temperature to 10 degrees Celsius, waited another 15 minutes to be sure that the temperature is stable. And now I already started the measurement. We are recording the OCP potential. This is stable at 3.236 volts, and I accepted this value. Now we started the impedance measurement at the OCP potential. You can see that the first frequency is already applied. These are the 80 kilohertz. And again, we have the 4 plots, 2 Nyquist plots. The first Nyquist plot for the cathode material, the lithium iron phosphate. Then the second Nyquist plot is the anode material, it's the lithium metal. And we have also the 2 other Bode plots for the electrodes. Let's have a look at the parameters we use for this measurement. The first frequency is the same as before, it's 80 kilohertz. The last frequency is 100 millihertz, and the amplitude is also 10 millivolts to keep the battery in a steady state. The measurement is running, the plots are building up, and we also merged the both Nyquist plots. So we have in blue the Nyquist plot of the cathode material, and in orange the Nyquist plot of the anode, the lithium metal anode. And you can already see that the diameter of the semicircle of the cathode is comparable small to the diameter of the semicircle of the anode. So the anode contributes much more to the total impedance of the cell than the cathode. And also this measurement will be finished in a few minutes. So the measurements are finished and we can have a look at the data. Let's go first to the 2 electrode measurements, which are measured in advance of this webinar. The plots are displayed in the upper part of this slide. The higher temperature leads to a lower impedance of the battery. This is clearly visible by the reduction of the diameter of the semicircle from 10 degrees blue to 22 degrees yellow. The diameter of the semicircle gets smaller, more than 100 ohms. This broad semicircle consists of 2 merged semicircles, one for the charge transfer reaction and one for the solid electrolyte interfaces. By zooming into the high frequency range, we discover a shift of the starting point of the curve from 21 down to 80 ohms. This is due to the improved conductivity of the electrolyte at the higher temperature. I did an evaluation of the measurements at 10 degrees Celsius, the blue curve, with the displayed equivalent circuit on the right side. During the fit, all values of the circuit elements are determined. They are displayed below each element. And now it's getting clear that with impedance spectroscopy, all the values for electrolyte conductivity, charge transfer reaction resistance, resistance of the solid electrolyte interface layers, impedance caused by diffusion can be quantified. I need to mention that the cell is a deeply discharged lab cell, so it is not optimized, as you can see by the relatively high impedance values. To have a detailed view which electrode or which process contributes to the total impedance, we did the 3 electrode measurements, which are displayed in the lower plot. It can easily be deducted that the anode contributes the most to the impedance of the cell, and the temperature decrease from 22 to 10 degrees Celsius also increases the impedance values of the anode. Unfortunately, due to an artifact, the values of the cathode, the purple and the blue curve, can't be evaluated in our measurement. That's life, and the next step would be to assemble a new battery and to repeat the 3 electrode measurements again to get all values for the anode and cathode processes separately. So, in this video I gave you a brief overview about impedance measurement on lithium-ion batteries. We had a look at important practical issues we have to consider doing impedance measurements, and at the end we did measurements at 2 different temperatures. If you have questions or recommendations, send them to sandro.haug@metrohm.de. You can find more information about electrochemical applications in the application finder on our website or on our blog Analyze This. So take care and see you soon.